So now we look at something shorter and quicker, like just models of motion quickly. After that's all those examples of separable equations and such. This also uses some separable differential equations to solve, but it looks at mainly Newton's laws of motion and such are involved here. And of course, I would draw a model. You can draw it out, but since these are like one-dimensional, it's not extremely important that you be able to draw these perfectly as long as you understand what's going on. Especially in some of these, like where it's very quick. You could draw these out. Just if a person wanted you to draw a quick sketch, you could, but it's irrelevant right this second. Just to look at the mass is what's most important first of all. So, and any sketch is just a way to help you understand what's going on. But so you have the acceleration due to gravity is 9.8 meters per second squared. It's near the Earth's surface. It's exactly that. It varies a tiny bit. Like on Mount Everest, it's a little bit different, but still pretty close. It's good for a basic mass like this to look at. So if a rocket ship in free space were able to maintain this constant acceleration indefinitely, how long would it take the ship to reach a speed? A speed equaling 1/5 c, where c is the speed of light. How far will the ship have traveled in this time? So we want the distance traveled, which is x, is distance traveled by a ship I'll have in my model. And we want the actual time. So ignore air resistance. We're not going to do any involving air resistance. So the speed of light is 3.0 times 10 to the 8 meters per second. So we know v equals dx dt and acceleration, velocity equals dxt and acceleration a equals d squared x dt squared, which is equal to, of course, as well the derivative of velocity, so dv dt, always expected time. So that's important. So acceleration equals dv dt. And I use tf t0 right now, but you can just use t and t0. And the same vf v0 can just be v and v0 because that's what it will be in like most models and stuff, but I end up using it anyway. So basically you integrate. You have a, you put dt on the left side and dv on the right side. It doesn't matter, just two different integrate. You have to integrate them separately. So a dt, the integral of that, it's a definite one, so no constant, so we'll see. We have a times tf minus t0 equals to vf minus v0. And you can just say t minus t0 and v minus v0, but we assume that initial time is 0, like almost all. You usually almost always do that because when you start something, you're doing it from the frame of reference that time is 0, and that the time you finish at is your time, or tf in the first thing. And here we assume v0 is relevant sometimes, but here we're going to assume it's 0 as well. That's a common thing as well. So really it's just a times t equals v. Because t is 0, t0 is 0, and v0 is 0. And you can solve for t just by dividing by a. So t equals v divided by a. And we have our values of, we have a equals 1/5 c. Assume, wait, no, not v. We have v. We want velocity to equal 1/5 c we want to find what time it is. And we have a, which is constant, which is 9.8 meters per second. Plug in the value of c, and your units will cancel, so you just get time in seconds. So when you put in the calculator, you get 6.12 times 10 to the 6th power seconds. Then you have to solve the distance. We know v equals at, t equals 6, and v equals dx dt is now what we want. So dx dt is equal to at because we know v equals at as well from this part. And we can solve both. We separate the variables and we get, so similar to before, it's x and x0 and t0. I put it. We're integrating by, and we assume that x0 the point of reference, like t0, so it's 0. x0 equals 0, t0 equals 0. X is, it starts at 0 basically, so that's why. So it's just x minus x0, so it's x equal to a times t squared divided by 2. Because it's a times, t squared, basically t squared minus t 0 squared, so it's like just t squared. And it's divided by 2. Because the integral of just t is t squared over 2, so that's why it works like that. So x equals 1/2 at squared. Simply to rewrite it like that. And then you just 1/2 times 9.8 meters per second squared times 6.12 times 10 to the 6 seconds squared. And you get 1.84 times 10 to the 14th power meters. And that's, your answer. It'll travel that far and it'll take that many seconds. Here's of course you can definitely draw this one out. Another thing, but you'll see what we assume when we have gravity and stuff. But stone is released from west and dropped into a deep well. 8 seconds later, the sound of the stone splashing into the water at the bottom of the well returns to long text. You release how long does it take the stone to drop to the bottom of the well? All in down. How deep is the well? So you want to find depths of well and how long it takes for the stone to drop to the bottom of the well. And you're given the speed of sound as 340 meters per second. And released from rest means that it starts at velocity of 0. So here's something we have to consider. F equals mass times acceleration, which is equal to m times dv dt, which is equal also to m times d squared x dt squared, which is equal to, and it's all equal, and force is equal to all of these. These are just different ways of writing it, and also negative mg, because it's equal and opposite. That's one of Newton's laws. F equals ma, and it also equals negative mg, because it's gravitational oppose acceleration. Point is that we can cancel out all these m's. But what we really want to get from this, like you can look at that, dv dt is equal to d squared x dt squared, which is equal to negative g. That's what we really want to look at. We divide out m. We can basically divide out mass for this. That's why I'm not given any mass. But mass does not count for in these pretty ideal situations where you don't have air resistance or anything else involved. That's why mass can be abandoned. So we basically want to look at dv dt equals negative g, and it's like that because it's basically pulled downward negative g. Now the difference is, we'll see in a minute, but first let's just solve for dv dt equals negative g. That means we have v and v0 and t0 we integrate by on both sides. So dv negative g dt. So v minus v0 equals negative gt, and of course v equals negative gt plus v0. We can just do this, and then we can replace v equals dx dt. We can put dx dt because that's what it's also equal to, and then we can integrate again, separation again. Negative gt plus v0, and ideally we'd be able to do that, and we'd have x equal to negative 1/2 gt squared plus v0 t. But v0 is equal to 0, so we eliminate that part. So it's x equals negative 1/2 gt squared, which equals, negative 1/2 g, 9.8 meters per second squared, t squared. So it's negative 4.9 meters per second squared times t squared, basically. But for this problem, we can just say 4.9 meters per second squared, because you're dropping it, so acceleration is in the same direction. So negative is not needed, basically. Like, it's all going in the same direction from start to finish, basically. That's how I think of it, at least. And we also know that 8 minus t seconds are required to hit bottom of well, because it's heard 8 seconds later. That's one of the things. Takes 8 seconds later, sound. So x equals 340 meters per second times 8 minus t is another expression for x. Then we have to set these equal to each other. So we have to solve for t here. It becomes a quadratic equation. We solve that. You can do all the math here. It's just plug into a calculator and make sure you do it right. T equals 7.24 or t equals negative 76.63. We can't have negative time in our world. So it's just 7.24 seconds to drop to bottom of well. And that's how math in this type problem works. Showing it. X equals 340 times 8 minus t. We have to find x now. We can use one of these expressions for it, but So you plug in 7.24 for t, and you get 258.4 meters. So depth of the well is approximately 258.4 meters, which sounds reasonable. I assume a couple hundred meters is not, is pretty reasonable for a well. It's a relatively deep one, but it's not like ridiculous. So you need to get your water somehow. Okay. So it's similar to the last one. A body is released from rest and travels the last half of the total distance fallen in precisely 1 second. How far did the body fall, and how long does it take to fall the complete distance? Ignore air resistance. So we have it all in the same direction. So negative, positive. It's all going to be positive. We'll take going down, like falling down in the last one. We take it as positive. You really want to get into specific nuances. You could draw it out and just say that the positive y-axis, it's on the one axis, the y-axis. Let's say for dropping down, the positive is downwards, negative is upwards, basically. However you want to draw it out, if you really want to draw it. I don't think it's necessary for simple ones like this, at least. You always draw it out. Now, if we're working in 2 dimensions, especially, it'd probably be better sometimes to draw those out when you get angles and all that. Well, but not for this stuff. So yeah, we're not going to do a lot of the nuanced things for this one, especially because we kind of already figured out the mass for the equation we're going to use. X equals 1/2 gt squared plus v0t, and v0 equals 0. So x equals 1/2 gt squared is an equation we'll use. That was the last half, and g is gravitational acceleration, of course, towards Earth. So that's when I specified out, it's 9.8 meters per second squared. That's always going to be involved whenever you have the Earth working against you. Force of Earth. You have the acceleration due to gravity. So g is. For anything that takes place on Earth, we'll have that value as an approximate formula. So the first half of this distance. First half is x equals 1/2 gt squared, and t equals time of first half. So the total distance covered by the body is 2 times x times t plus 1. So 2 times x is the total distance. T plus 1 is total time. So 2 times x equals 1/2 g times t plus 1 squared is another thing we have. And so we just plug in 1/2 gt squared into the equation. That's one way we can solve this, at least one way. And so it becomes gt squared equals 1/2 g times t plus 1 squared. Divided by 1/2 g, both sides, we get 2t squared equals t plus 1 squared. 2t squared equals t squared plus, because we just FOIL it, or whatever you want to call it, t plus 1 times t plus 1 is t squared plus 2t plus 1. And we simplify down, so everything's on left side, and we have equal to 0, and we do quadratic equation again. Very, very common. You have to know the quadratic equation by heart. Quadratic formula. We have to solve for the quadratic equation. So t squared minus 2t minus 1 equals 0 is what we end up with. And we solve for that, and we eventually get t equals 2, because we can plug in all the parts, because t is the only unknown variable, and we can solve. So eventually we get t equals 1 plus or minus square root of 2, so that means t equals 2.414 seconds, or t equals negative 0.414 seconds, I believe that is, and you can't have negative time. Time is a positive value in our universe. You can't go back in time or any of that stuff. Can't have negative time. So t plus 1 is equal to 1 plus 2.414 seconds, so it's 3.414 seconds. And that's the time for a complete fall. How long did it take to fall? So how far did the body fall? Now do we know complete time? Well, 2 times x equals 2, so we have 2 times 1/2 gt squared. That's equal to just gt squared, so 9.8 meters per second squared times 2.414 seconds squared. Yeah, we're using this form, the 2 times x form, so we just use gt squared. So we get gt squared equals to, which is our answer, 57.11 meters. So 57.11 meters is how far the body fell. And it took 3.414 seconds for the full fall. Yeah, the t plus 1 is because, the total time, but just in case I didn't mention it, t plus 1 is because it says it took half the time, exactly 1 second. The second half. And we assume the first half time is t, so t plus 1 is total time. What, if anyone was wondering what it. Finally, a particle moves along a line with xv and a representing position, velocity, and acceleration respectively. Assuming that the acceleration a is constant, use equation 3.15 to show that v squared equals v0 squared plus 2a times x minus x0, where x0 and v0 are the position velocity of the particle at time t equals 0 respectively. So that's, and then a car's speed is reduced from 60 miles per hour to 30 miles per hour in a span covering 500 feet. Calculate the magnitude and direction of the constant deceleration. So negative acceleration. Yeah. It's obvious it's going to be negative in that case. So in the book it says equation 3.15 is given as a equals dv dt, which is equal to dv dx times dx dt, which is equal to dv dx times v. Point is that it wants us to look at a equals dv dx, because that's what we can convert into it, or dv dx times v. This is something we can integrate by separating variables like the other ones. So this is the first half, just solving this. So we have integral x0 a dx equals v v0 integral v v0, like from that distance v0 to v, v0 to v and x0 to x are things we want to integrate by, so it's v dv here. Oh, and we're going to so we're not assuming, yeah, we don't assume it's equal to 0 here, so that's why we have to definitely include it. So a times x in brackets x0 and v squared over 2, since it's v dv, integral it's v squared over 2, v v0. No constants because these are exact integration, like all of them. So it's a times x minus x0 equals v squared minus v0 squared divided by 2. We plug it in. 2 times a times x minus x0, because we multiply by 2 on each side, equals v squared minus v0. And you continue on. Yeah, you basically just add v0 squared to the both sides. You get v squared equals v0 squared plus 2a times x minus x0. That's it for that part. And then, so we have that equation, and we have v0 equals 60 miles per hour. It's given. And v is equal to 30 miles per hour, and x minus x0 we just assume is 500 feet because it gives us that, so just the expression. That's the distance covered. That's how to think of x minus x0, it's just the distance covered. So regardless of whatever x0 is, the difference is at 500 feet. X minus x, that's what we think of sometimes when we assume x0 is 0 a lot of times. That's basically the unofficial way of doing it. X minus x0 is literally just the distance covered, so 500 feet. Between one point to another point, so 500 feet times, how I did it was I did a lot of unit conversions here, so as you can see on this, that's why it took up a lot of space. This one was by itself. Otherwise it's a very quick calculation if you had everything in the same units and stuff. So 500 feet times 1 mile divided by 5,208 feet. That gives us 0.0947 miles. So we can just calculate from here and then convert it more after we get a final answer for the acceleration. You plug it, so you can just solve for acceleration first by making it v squared minus v0 squared divided by 2 equals a times x minus x0, so you divide by that. You get this form, and then you plug in everything. 30 miles per hour squared minus 60 miles per hour squared divided by 2 times 0.0947 miles. And then you have just keep on calculating, plugging it in, everything. I show some steps here. But you get negative 14,255.5 miles per hour squared. And that's a little, we might want to change the unit because it's only 500 feet distance. So I want to lower the unit in terms of feet and seconds, I guess, is one way that they can want it. So feet per second, so we just do negative 14,255.5 miles per hour squared. We multiply by 5,280 feet in 1 mile. That's the normal conversions. And multiply by 1 hour squared. So in 1 square hour, we have 3,600 seconds, 3,600 squared seconds squared. Those square seconds, you know. Because there's 60 seconds in a minute and 60 minutes an hour. So in a normal hour, it's 3,600 seconds. Well, we have to square that when we square the seconds. Conversion. That's how it works. That's just a cool example to show off. So negative 5.81 feet per second squared. There, that sounds more reasonable to understand in terms of it. So acceleration equals negative 5.81 feet per second squared. That's a constant deceleration. Magnitude direction, it's the opposite direction of the movement, obviously. Just slowing down. Magnitude's negative 5.81. The magnitude's 5.81 feet per second squared. Direction is the negative sign, shown its opposite to what the original. Because this is one-dimensional space, so it's really going from left to right or up and down, basically. So it's the opposite of what it was going. Slowing down, basically. I always think of it.